Hello and welcome back, live with another competition update for Hackasat. I'm your host, Jordan Wines. First, let's take a quick look at our current scoreboard, which at this point should be pretty familiar to everyone. Since our last update an hour ago, we've actually seen no movement on the scoreboard yet. Challenge 4 is proving to be difficult for the teams, as we predicted it would be. But from the sound of it on the team chats, they might be getting a little closer, so hopefully we'll see some movement soon there. While we wait a little bit more game action, let's learn about the complexities of navigation in space from our resident expert, Jess Coffey, in another episode of Space Talk.
Now that we've seen how precession takes place, let's try to predict its direction in this case.
Nice to be in orbit.
So, how do satellites know where they are? There are actually two completely separate dimensions that we need to consider with satellites. The first being orbital parameters. This describes the movement of the satellite over time, kind of like referencing a flight plan to tell where a plane is. The second is the attitude. Basically, what direction am I facing? This is entirely independent of location for satellites because there's no natural state that it's expected to be in. On Earth, that natural state is aligned with gravity, basically upright, and satellites have no force or no natural state to adhere to. Figuring out the orbital parameters of a satellite requires taking several observations and deriving them. One way to obtain these observations is to use the same technology we use here on Earth, an onboard GPS receiver. Additionally, we can look for them through external sensors. NORAD tracks all objects in space through the United States Space Surveillance Network, primarily using radar. Each object in space gets a unique ID assigned to it called a NORAD ID, which is universally used by satellite operators to reference it. NORAD uses these observations to derive the orbital parameters and uses two-line elements, or TLEs, as a standard for providing all the orbital information. Here's an example of one for the International Space Station. You can see the ISS's NORAD ID at the beginning of each line, 25544. The rest is used to describe the orbital motion. This TLE is simply an estimation of the orbital trajectory, and there are inherent inaccuracies. The way we propagate orbital trajectories introduces an error that becomes significant over time. The TLE format accounts for this by having a timestamp, or epoch, built into it to indicate when it was taken. It is then valid for only about a week or two around that epoch, depending on how important accuracy is for that specific satellite. As a result, they must be constantly updated to keep from going stale. Now we know our orbital parameters. What about the second category, attitude? Space is full of a lot of nothing, but there are still a few somethings that you can sense. The most common sensors are magnetometers, sun sensors, and star cameras. Magnetometers are used by satellites when they are within Earth's magnetic field. This is a very low fidelity measurement though, so it's typically not used by itself. Sun sensors are photodiodes that measure light intensity. By putting these sensors in several places surrounding the satellite, we can measure sunlight on each sensor, giving us the direction of the sun. That, combined with location data, can give us a pointing accuracy of 10 degrees or less. And finally, star cameras are the primary means of precise attitude measurement. Stars are far enough away from us and moving slowly enough that we can treat them as constant for all but the highest precision tasks. This means we can create a map of the star field that surrounds Earth, and we can reference it to calculate exactly where a camera mounted on the satellite is pointing. Now that we have determined our orbital parameters and orientation, we have a natural follow-on question. How do I change them? Getting around in space, meaning both changing your direction and changing your orientation, are difficult primarily because there is simply very, very little to work with. All the modes of transportation here on Earth require exerting a force on your external environment. Cars push their tires against the friction of the roadway, planes pull air through their engines, and ships push water with their propellers. Again, satellite orbit and satellite attitude are generally disconnected, so we have to control them separately. First, we'll cover how do I change my orbit. In orbital motion, we don't actually point to where we want to go and start moving there. Satellites are already moving at a tremendous speed, around 17,000 miles per hour in low Earth orbit. Changing orbit in space actually consists of carefully adding and subtracting energy at the right times. Not electrical energy, but rather the satellite's combined kinetic and potential energy. Adding energy raises the orbit farther away from Earth, and subtracting brings you closer. Notice I didn't say going faster raises the orbit, because as you get farther away from Earth, you actually slow down due to the properties of orbital dynamics. So we'll stick with the term energy. Since the satellite already has so much energy that it acquired from launch to stay in orbit, most changes are very small by comparison, raising or lowering orbits to maintain or change certain orbital characteristics a small amount. There are all kinds of technologies being developed and in use to add and subtract energy from satellites, but the most common are thrusters. Thrusters exist to eject fuel out of a spacecraft fast enough to change its momentum significantly. This is the same way rockets work, and it comes from one of the fundamental laws of physics, conservation of momentum. There are several different types of thrusters for spacecraft that each have different trade-offs, but all of them operate on the core principle: throw stuff out the back really fast. There are cold gas thrusters, which are the simplest ones. They released compressed air to generate a small amount of thrust. There are chemical thrusters, or miniaturized rockets, that are harnessing a chemical reaction to energize and release fuel to generate thrust. And finally, there are ion thrusters, which use electromagnetic force to control, accelerate, and release charged particles to generate thrust. Now, how do I control the attitude? Satellites again have the problem that they exist in a literal vacuum. You can't change your direction with a steering wheel, rudder, or flaps. To tackle this, they actually make use of the same law of physics, but with a slight twist: conservation of angular momentum. This one is easier to demonstrate in your daily life. If you ever spun yourself on a chair, you probably realize that pulling your arms in will make you go slightly faster. This is a demonstration of that law. Satellites make use of this through a technology called reaction wheels. The core concept is there are very small wheels contained within the spacecraft, and if you spin that wheel very, very fast, you'll cause the spacecraft to react and spin in the opposite direction. The motors that spin that wheel need to exert a torque to make that happen, and the same opposing torque is then exerted back on the spacecraft, causing it to spin as well. All of these technologies put together that allow you to determine the orbit, determine the attitude, and control the orbit and control the attitude make up the satellite's Attitude and Orbital Control System, or AOCS, which is the most complex subsystem on most satellites.
Thanks, Jess, for that update. Before we sign off here, I want to give another update on the progress of the on-orbit mission. Remember, we chose a single team solution to send to our orbiting satellite. The ground control team is telling me that we have those commands scheduled to be sent between 1 p.m. and 4:30 p.m. Pacific, and we are just now starting that comms window. Given the orbit predictions of our satellite and the moon, we expect the actual photo to be taken around 6:30 Pacific this evening. With any luck, we expect to receive that moonshot back here at Earth at 1 a.m. Pacific tonight, and we'll have it for you tomorrow at the closing awards. That's it for this hour's update. We'll see you back here at 4:45 Eastern, 4:50 Eastern, 1 p.m., 1:50 Pacific for a final hourly update before our end-of-day recap tonight. Thanks and have a good one.